Our technologies are simply noisy. From the way we transport ourselves across the world, to the generation of clean energy, flow-induced noise is everywhere. But who can we blame for this? One word: turbulence. No, not that turbulence, it's this kind of turbulence. Whether you're dealing with high-speed flows or large bodies, turbulent flow is always present. And depending on where the turbulence is coming from, there are two general classes of flow-induced noise. If turbulence is present in flow field, which then impinges onto an airfoil for instance, then this is referred to as turbulence interaction noise. This process can be found inside a turbofan, where the turbulent fan wake impinges onto the downstream stators. Nonetheless, the airfoil itself can also produce turbulence in its boundary layer, and later noise is produced as the turbulent boundary layer flows past the trailing edge. This turbulent boundary layer trailing edge noise is one of the main noise generation mechanisms in modern wind turbines. As you can see, noise is produced when turbulence encounters sudden transition in the flow field, from the free fluid to a solid body, or vice versa. Instead, a smooth transition perhaps would help with noise reduction. And fortunately, there is a material that is sort of in between a fully solid or fluid. Those are porous materials. In the following, you will find two applications of this aluminum metal foam for aerodynamic noise reduction. This is a rod L4 configuration. The rod leaves a trail of vortices known as the Kármán vortex thread, which then impinges the NACA 5006 airfoil. The periodicity of the vortices combined with the many scales of turbulence in the rodway, resulting in the radiation of tonal and broadband noise. By using the metal foam leading edge, the broadband noise can be reduced by up to 3 decibels, but the tonal noise is relatively unaffected. Nevertheless, this can be improved further by adding a serrated platform. In fact, the porous serrations perform better in terms of noise reduction compared to the regular solid serrations. In this case, the porous material reduces the severity of the vertical distortion near the leading edge, which in turn decreases the noise source intensity. In another case, we have a NACA 0018 airfoil. Tripping devices are installed near the leading edge to produce turbulent boundary layer. The trailing edge segment of the airfoil is replaceable with an insert made out of metal foam. In doing so, the noise emissions is reduced by up to 10 decibels at low frequencies, although it is also accompanied by slight noise increase in the high frequency range, which has been attributed to the rough surface of the metal foam. It has been found that noise sources are distributed along the porous insert surface, although the strongest ones are located at the solid porous junction and at the actual trailing edge. Despite this, the porous trailing edge has lower scattering efficiency compared to the solid one, leading to noise attenuation. To summarize, porous materials are very promising for mitigating flow-induced noise. However, there are questions that remain. How to upscale these laboratory studies to the real thing, and what are the optimization strategies based on the porous material properties? With that being said, this topic is still under active investigation, and to learn more, please have a look at the list of references at the end of this video. I'm Christopher Truna of the Aeroacoustics Research Group under the Wind Energy section, signing out.